to Wilson Lab. I'm Katie Mooring, Chess Operations Manager, and this is Kate Shanks, Chess Staff Scientist. We are currently 40 feet below the Cornell University campus at the Cornell High Energy Synchrotron source. Kate and I would like to talk to you about our roles here at Chess and how we ended up working at a particle accelerator. But first, check out this video.
Despite centuries of scientific contributions and the development of technologies like those that you are about to see, many unanswered questions still prevent us from fully understanding the complexities of our universe. What is the universe made of? How do we make energy storage more efficient? What causes metal to fatigue and fail? What makes one virus deadlier than the next? Students and staff here at the Cornell Laboratory for Accelerator-Based Sciences and Education, or CLASS, have been pursuing these questions for more than 50 years, developing new technologies, pushing the frontiers of science, and improving the lives of millions. To do this, we have designed one of the most powerful particle accelerators in the world, right here in the Wilson Synchrotron Laboratory. The accelerator complex creates electron and positron particles and accelerates them to near the speed of light. Initially designed to smash these particles together, it is now finely tuned to generate an intense beam of light that is used to study matter at the atomic scale. This light is called synchrotron radiation. 40 feet below the Cornell campus, positrons are created and pulled into a linear accelerator, or LINAC, where a driving radio frequency is timed to energize and accelerate the particles in a straight line. Once the positrons leave the LINAC, they enter the booster synchrotron, which is similar to the on-ramp of a highway. The positrons travel through radio frequency cavities where they interact with radio waves, getting hurled forward faster and faster until they approach the speed of light. When the positrons reach the desired energy, bunches are transferred into the particle superhighway, the Cornell Electron Storage Ring, CESAR. Electromagnets steer and focus these particles into a circular path, while waves push them like surfers on the ocean. In CESAR, they travel around the half-mile ring at a rate of 400,000 times every second. Special magnets, called undulators, subtly disrupt the path of the positrons as they travel through CESAR. This disruptive process results in the emission of an intense beam of light. The light, in the form of X-rays, is directed down a separate beamline while the positrons continue around the storage ring. Beamlines and experimental stations called hutches make up the research facility called the Cornell High Energy Synchrotron Source, CHESS. A variety of optical instruments, such as beam splitters and mirrors, are set up along the beamline to adjust and focus the path of the X-ray in order to create the desired characteristics necessary for each experiment. CHESS X-ray beams are about 100 million times more intense than those produced by X-ray machines in a medical doctor's office, and can be used to image materials at the nanometer scale. Scientists come from all over the world to examine their samples with our X-rays. They might bring artifacts, protein crystals, batteries, solar cells, artwork, or other materials. When the X-rays hit a sample, they are either absorbed or scattered. A state-of-the-art detector collects and records the scattered X-rays coming off the sample. And from this information, scientists can learn about the structure and elemental composition of the sample. They can follow how the sample changes under intense pressure and strain. This kind of information is extremely valuable in understanding the world around us. There are more than 60 synchrotron radiation facilities worldwide. However, there are only 5 like ours. We'd like to welcome you to Wilson Lab. We're delighted to have you join us on the journey to better understanding our universe.
Welcome to the Forming and Shaping Technologies beamline on the experimental floor. So this is where the science happens. You just heard a bit about how CHEST has different beamlines. So each beamline has a different science mission and a different set of capabilities. So I'm the lead scientist here at the FAST beamline, which is focused on investigating what we call structural materials. So that's materials like metals and concrete and rocks that are used to bear mechanical loads. You can find structural materials in airplanes, in medical devices, in roads and buildings, really all throughout everyday life. So we've even tested cements that could be used on the moon. So in college and grad school, I studied physics, but growing up, I actually didn't think of myself as someone who liked science or who was particularly good at it. Something clicked for me when I took a required physics class in high school. And I started to see, in a way I hadn't before, how measurements that we made in lab exercises connected to the theories and equations that we learned from the textbook. And I got really interested in this way of learning about the physical world through experiments. And now my job is working with other scientists to make their experiments successful and to find ways to do new types of experiments that weren't previously possible, whether it's measuring things faster or in more detail, or whether it's investigating brand new technologies like the 3D printing of metals.
Kate is a great example of a CHEST staff scientist. There are dozens of scientists like Kate that work at CHEST, and there are just as many, if not more, technical staff that work here as well. As operations manager, I oversee the technical staff whose main responsibility is to keep the machine and experimental equipment functioning properly and support the research that is happening here. Basically, we solve any technical problem that comes up. Our team comes from a variety of backgrounds, some with 2-year technical degrees and some with their masters, some with degrees in physics and biology, and others in mechatronics and mechanical engineering. The work we do includes modeling, designing, and maintaining experimental equipment, enabling equipment and hardware to be able to talk to each other and be controlled remotely, overseeing the safety of the staff and researchers, and maintaining the infrastructure that surrounds us. Even though our backgrounds are different and our areas of expertise are varied, we all share some common qualities. We want to understand how things work, we're good at troubleshooting, we are problem solvers and innovators. Most of the technical staff who work here didn't start their careers knowing that they wanted to work at a synchrotron. I know I didn't. I have a bachelor's degree in biology, and after college, I worked for about 2 years in the chemistry department of a materials testing lab. I started to get bored with doing the same test every single day. I wanted to learn more, to be challenged, and to work with people more. I applied to a job at CHEST without knowing anything about the lab, but excited to learn and try new things. That was 10 years ago. In my time here, I've worked in various areas supporting research. As part of our safety committee, working on ultra-high vacuum systems, training new support staff, and so on. Now I'm the operations manager for CHEST. My current responsibilities include overseeing the daily operations of our research program, coordinating with the CSER operations group who run and maintain the accelerator, and supervising about 10 of our research support staff. If I had a piece of advice for young people looking to get into science, it would be to keep looking for ways to challenge yourself. Don't be afraid to try something new. If you don't succeed the first time, you'll still learn from it.
There's no one way to be a scientist or an engineer or a technician. We all have different strengths, and success comes from working together and combining those strengths to do more together than we could do alone.
If you'd like to learn more about CHEST, you can visit our website at chest.cornell.edu.